Hey everyone, and welcome. Today, we're going to break down three data structures that are, honestly, the bedrock of computer science: the stack, the queue, and the Deque. If you're doing any kind of coding, getting ready for interviews, or you're just curious about how software really works, this one's for you.
But let's start with a question. You ever hit undo on your computer and just wonder, what's happening under the hood? How does your machine remember the very last thing you did, and the one before that, and the one before that, in perfect order? Well, the answer is one of these simple, super elegant structures we're about to cover.
All right, let's dive right in, starting with what I think is the most intuitive of the bunch, the stack. The idea behind it is incredibly simple, and you see it in the real world all the time.
So, a stack is all about one guiding principle: last in, first out, or LIFO for short. The best way to picture this? Think of a stack of plates at a buffet. You put a clean plate on top of the pile, and when someone needs a plate, they grab one right off the top. The last plate you added is always the very first one to be taken.
A stack really only does two main things. When you add an item, that's called a push, and when you take that top item off, it's called a pop. Now here's the crucial part to remember. Both of these actions, push and pop, happen at the exact same end, the top of the stack. That's it.
So where do you see this in action? Oh, pretty much everywhere. It's the magic that powers your browser's back button. It manages how programs keep track of function calls. And yep, it's exactly how that undo feature works. Every change you make gets pushed onto a stack. When you hit undo, the program just pops the last action right off. Simple as that.
Okay, so let's move on to our next structure. If a stack is all about last in, first out, the queue is, well, it's the complete opposite. A queue is all about fairness.
A queue runs on a first in, first out principle, or FIFO. The perfect real-world example here is just a line at its whole booth, a line at the grocery store, you name it. The first person to get in line is the first person to get served. It's the definition of orderly.
So the terms are a little different here. When you add something to the end of the line, it's called NQ. And when you remove the item from the very front, the one that's been waiting the longest, that's called DQ. So you see the difference, right? Unlike a stack, a queue is a two-way street. You get in at one end and you get out at the other.
And this FIFO behavior is absolutely essential for so many things. It's how your printer handles multiple print jobs in the order you sent them. It's how a web server juggles tons of requests without losing its place. And it's a fundamental piece of how a computer's processor decides which task to work on next.
So we've got LIFO with the stack and FIFO with the queue. But what if you want both? What if you need the best of both worlds? Well, that brings us to the Deque, which is this powerful, super versatile hybrid of the two. A Deque, and you'll hear it pronounced Deque, is a double-ended queue. And it's pretty much exactly what it sounds like. It's a collection where you can add or remove items from either the front or the back. The two-way alley analogy here is perfect. Stuff can go in and out from both ends, no problem.
Now this is where it gets really cool. Check out its flexibility. If you take a Deque and you just decide, okay, I'm only going to add things to the back and take things from the back, what have you just made? A perfect stack. You get that exact same last in, first out behavior.
But wait, there's more. Using that same exact structure, what if you decide to add things to the back, but take them from the front? Boom! You've got yourself a fully functioning queue with perfect first in, first out behavior. One single data structure can act like both. Now that is powerful. All right, let's get to the part that really matters, especially in a technical interview or when you're writing code that needs to be fast. Let's talk about speed, costs, and some of the hidden traps you need to look out for.
This slide right here is key. For all three of these structures, the main operations, adding and removing things from the ends, are incredibly fast. We're talking O of 1, or constant time. But you might notice that little word in there, amortized. What on earth does that mean?
Well, amortized means that most of the time, the operation is practically instant. But every now and then, the structure runs out of space and has to resize itself to make more room. That resize operation is slow. It's O of n. But because it happens so rarely, that expensive cost gets spread out, or amortized, over all the super cheap operations. So on average, the cost is tiny.
And this brings us to a huge, massive interview pitfall, especially in Python. If you try to use a regular list as a queue, and you remove an item from the beginning using pop0, you've just fallen into the trap. That is not a fast operation. It's slow, it's O of n, because after you remove that first element, every single other element has to be shifted over. For a large queue, that is a performance nightmare.
All right, let's pull all of this together. Think of this as your quick and easy cheat sheet. When you're in an interview and you have to make a decision, here's what you need to remember. It really boils down to just one question. In what order do you need to process things? If you need to handle items in the reverse order they came in, like an undo history, you need a stack. Last in, first out. If you need to handle them in the exact order they arrived, like a printer queue, then you need a queue. First in, first out.
So when do you pull out the powerful deck? You use it when you absolutely need that fast O1 speed for adding and removing items at both ends of your collection. That specific need for flexibility at both the front and the back is the telltale sign that a deck is your answer.
Which leads us to a final thought for you. Now that you know the rules, LIFO, FIFO, and the flexible hybrid, which of these structures do you think powers a sliding window algorithm? You know, the kind of problem where you need to constantly add a new element to one end of a sequence while removing an old element from the other. Figuring that out, well, that's when you know this stuff has really clicked.